For 100 years, science told us nothing could outshine the cosmic dark ages, the universe's silent, starless dawn after the Big Bang. But in James Webb just looked beyond the Big Bang allow, that certainty collapses. The James Webb Space Telescope has spotted gigantic, blazing galaxies and mysterious light beacons where only emptiness was supposed to exist, some less than 300 million years after time began and 9 even deeper, closer to the beginning than theory allows. If these results hold, everything we think we know about the universe's birth is suddenly up for grabs, and pointing to cosmic forces no one predicted. So what exactly did Webb see, and why does it threaten the universe's rulebook? The universe began as a furnace of unimaginable heat and pressure, but after the first flash faded, a deep hush settled across the cosmos. Hydrogen and helium, forged in the Big Bang, drifted as a vast invisible fog. There were no stars, no galaxies, not even a single spark to break the silence. Only a sea of neutral gas, cooling slowly as the universe expanded. Temperatures dropped to just a few dozen Kelvin, barely above absolute zero. In every direction, darkness reigned, thick and absolute, with nothing to catch or scatter a photon. Space itself stretched wider and colder, pulling atoms farther apart until even the faint afterglow of creation faded to a whisper. Gravity moved in silence, gathering the first wisps of matter into denser knots, but this process took millions of years. For ages, the universe was a black ocean, each atom of hydrogen floating alone, untouched by light. In this endless night, time seemed to stand still. The only motion was the slow pull of gravity, working patiently, shaping the raw material of everything to come. This was the cosmic dark age, a time when the universe waited, frozen and silent, for the first light to break the spell. Simulations of the early universe have long predicted a slow, methodical build-up to the first light. According to these models, gravity began its work by gathering dark matter into invisible halos, dense knots that would serve as scaffolding for everything to come. Over tens of millions of years, these halos attracted the surrounding hydrogen and helium, drawing the gas into their gravitational wells. As more material fell in, the densest regions grew denser still, setting off a chain reaction that would eventually lead to the birth of the first stars. The timeline was thought to be rigid. Only when a halo reached about 100 million times the mass of our Sun could it cool enough for stars to ignite. The first true star clusters, what astronomers call population 3, were expected to appear at a redshift near 10 or roughly 500 million years after the Big Bang. Anything earlier would require gas to collapse and form stars with an efficiency far beyond what the laws of physics seem to allow. Cosmologists imagined a universe where small structures formed first, merging slowly over time into larger and larger galaxies. This process, called hierarchical assembly, was supposed to be gradual and predictable. Simulations showed a universe where darkness gave way to faint pinpricks of starlight, each one a product of careful cosmic engineering. Every step was governed by the cooling of gas, the pull of gravity, and the slow accumulation of mass. In this blueprint, the cosmic dawn was a drawn-out affair. First light would flicker on, not in a sudden blaze, but as a faint glow that grew steadily brighter over hundreds of millions of years. The models set clear boundaries: no bright galaxies, no massive clusters, and certainly no complex structures before the universe was ready. The rules seemed unbreakable until new observations began to test them. JWST 14-0 stands out as the most distant galaxy ever confirmed by spectroscopic measurement. Its light began the journey to Earth just 290 million years after the Big Bang, captured by the James Webb Space Telescope at a redshift of 14.32. This isn't just a faint spark. Its ultraviolet brightness is measured at MUV -20.8, a level that rivals or surpasses far more mature galaxies. For context, astronomers expected the earliest galaxies to be small, dim, and rare, their stars only just beginning to form. Instead, JWST 14-0 appears as a cosmic heavyweight, already shining as brightly as many galaxies a billion years older. The confirmation didn't come easily. It took nearly 10 hours of the James Webb Space Telescope's most sensitive spectroscopic observations to lock down the galaxy's distance beyond doubt. The data revealed a clear Lyman break, a sudden drop in light at a specific wavelength, leaving no ambiguity about its place in cosmic history. The galaxy's half-light radius measures just 260 parsecs, making it both compact and intensely luminous. Its red ultraviolet slope suggests the presence of dust, meaning enough generations of stars had lived and died to enrich its gas, an unexpected level of maturity for such an early time. No simulation predicted a galaxy this massive and bright emerging so soon. In the standard timeline, this amount of star formation should have taken hundreds of millions of years longer. Yet here it is, forcing astronomers to reckon with a universe that built complexity far faster than models allowed. It's as if someone opened a baby photo album and found a fully grown adult staring back. Jade's GS-Z140 isn't an isolated outlier. It's the first confirmed sign that the early universe may have been anything but slow and simple. A team led by Pablo G. Perez Gonzalez at the Center for Astrobiology in Madrid has pushed the James Webb Space Telescope further than anyone thought possible, deep into the earliest moments of cosmic history. Using the deepest JWST/NIR cam imaging yet, reaching a faintness of 31.5 magnitude, they identified 9 mysterious light sources in a patch of sky that, by all rights, should have been empty. 6 of these objects appeared a redshift of about 17, and 3 more at a staggering redshift of 25. In cosmic terms, that means their light began its journey just 100 to 200 million years after the Big Bang, during an era long considered a cosmic blackout. The discovery relies on the dropout technique, which finds objects that vanish in bluer filters but shine in the red. The Lyman break, a sharp cutoff in a galaxy's spectrum caused by hydrogen absorption, shifts further into the infrared as distance increases. For these 9 sources, the break lands in the F200W and F277W filters, evidence that they exist at distances no telescope has confirmed before. The team's analysis combined data from MYDIS and NG Deep, stacking nearly 160 hours of exposure to reach the faintest galaxies ever detected. What makes these objects so startling isn't just their distance, but their brightness and apparent maturity. If these are galaxies, they are already forming stars at rates and efficiencies that defy every prediction. The ultraviolet slopes for several candidates are so blue, approaching beta of -3, that they hint at either pristine, metal-free stars or entirely new sources of energy. The number density is just as shocking. At Z approximately 17, there are about 10 to the -4.2 galaxies per cubic megaparsec, and at Z approximately 25, around 10 to the -5. This is 10 to 100 times higher than any model allows. No prior simulation predicted anything like this during the so-called cosmic dark ages. The standard rulebook said the early universe would be a slow, patient architect, assembling small clumps of matter over hundreds of millions of years before any real light appeared. Yet here are 9 beacons, burning through the fog when the universe was barely out of infancy. Their compactness, their extreme colors, and their sheer numbers all point to one conclusion. Something is happening in the early cosmos that current physics can't explain. These findings now demand new ideas, perhaps even new forms of matter or energy, to explain how the universe lit up so soon after the beginning. Andrea Ferrara, a theoretical astrophysicist, has spent years modeling what happens when primordial black holes, objects born in the universe's first moments, become surrounded by dense clouds of gas. His calculations show that even a tiny population of these black holes, each weighing in at around 10,000 times the mass of our Sun, could light up the early cosmos. The process is simple but profound. As gas falls into these primordial giants, it heats up and radiates energy, producing a steady glow. Ferrara's models suggest that if just 1 part in 100 million of all dark matter took the form of such black holes, the resulting accretion would match the number and brightness of the mysterious sources the James Webb Space Telescope has spotted at redshifts 17 and 25. These primordial lighthouses would have been scattered through the young universe, each one a beacon powered not by stars, but by gravity itself. Their existence would mean that the first sources of cosmic illumination weren't galaxies at all, but black holes feasting in the dark, rewriting the script for how and when the universe woke up. Some galaxies, even in the earliest JWST deep fields, spin more often in one direction than the other. In a sample of 263 ancient galaxies, about 60% rotated clockwise, while 40% spun the opposite way, a pattern that holds across independent surveys and persists at redshifts beyond 2. The odds of such an imbalance arising by chance are less than 2%. This hints at a universe with a built-in twist, challenging the old assumption that space looks the same in every direction. Cosmologists have debated whether this bias could be a relic of the universe's birth, or even a signal that the cosmos itself once spun. The idea is startling. If the early universe had a preferred direction, then cosmic symmetry breaks down on the largest scales. Some theorists go further, proposing that the universe could collapse inward in a future big crunch, or that our entire cosmos might be the interior of a rotating black hole. Others suggest we may live in a multiverse, where each pocket universe inherits its own spin. For now, only deeper spectroscopic surveys can settle what these patterns truly mean, whether they're cosmic accidents or the first traces of a grander, stranger order.